Right, welcome everybody to the Digital Manufacturing Centre. Great to have everyone here, and there's some tours arranged later on as well, so we'll show you all around for anyone that hasn't already been here. But great to have a digital and advanced manufacturing special interest group in real life, and great to have it here as well. So I'm just going to start this with a quick video, just for those who don't know what the Digital Manufacturing Centre is or may not have seen this video. I can't imagine most people have seen this before, but if this works, just to get you in the mood for what we're doing here. And I should point out all the rendering work, highly recommended. Something on the screen there, Pim. Yeah, right. And it does need an update because that says opening in March 2021. And I'm pleased to say we did open at the end of March 2021. So this facility's been open now since April and trading since April. And when you see what we're doing downstairs, we'll show you around. We'll give you a bit more of an insight into the technologies and stuff here. But I'm just going to run through very quickly some of the slides here. First thing to note is that we are a production manufacturing centre. So this is not about rapid prototyping, the old school only used for additive manufacturing. We're looking at scale and production manufacturing. And of course, that does mean that we can still make quantities of one. But for us, any quantity from 1 to 10,000 or 1 million is still production. It's all digitally driven and we have no tooling. So there's still the low volume opportunities, but we don't like to call it prototyping with low grade inferior materials. Just a bit of an update or background to the DMC journey. So the Digital Manufacturing Centre actually is a spin out from my other business, Kieron Special Projects. Kieron Special Projects was started back in 2012, and we quite quickly got involved in additive manufacturing, mostly around motorsport and composite tooling. And to cut a very long story short, we saw an opportunity to create a supply chain for additive manufacturing and scale up more than just organically, but make a step change. And so we set about building a plan for a standalone facility, and here we are today in a 20,000 square foot separate facility from KWSP, which is technology and sector agnostic. So we tend to work in sort of the high performance advanced engineering sectors at the moment. They're the areas that are adopting additive manufacturing perhaps the quickest: aerospace, space, motorsport, automotive. But we're also starting to see a large amount of activity in oil and gas and also consumer goods. So we're certainly starting to see rapid adoption of additive manufacturing across the board. And part of our USP on that is that we're also technology agnostic. So we're not tied into any particular machine or any particular supplier, but we do have some favorites. We have the ones that work best with us. And you will see machines downstairs from Renishaw, EOS, 3D Systems, Stratasys, and DMG Mori, and also Dimension. And we think that's a real advantage as well, because if we've come across a project where it doesn't fit any of those particular machine providers or technologies, we can go into the market and we can choose the right technology for that solution and invest in that. So we have a large amount of freedom. Normally, I'll go into a bunch of slides showing some of the equipment we've got downstairs. We'll give the advantage that we can go down and have a look and we'll get some tours. But what you will see downstairs is that there's a large presence from laser lines, and Mark and the team from laser lines are here today. We've worked with laser lines since the very beginning of our journey, and we're looking forward to also getting some more Stratasys equipment, the SAF and the Origin DLP equipment that will come in later this year that will allow us to service different products into new markets. And you'll also see the entire suite of Dimension. I'll point that out just so that when you go downstairs, you can look for it. But this allows us to do the really important bit around additive manufacturing, post-processing. So it's semi or fully automated post-processing for polymers. And you'll also see that for metals, we have post-processing capability, everything from CNC machining through to inspection, and also some heat treatment. And everything's digitally connected. So the advantage of this site, when we built it from the ground up, is that we We built it with the infrastructure in mind for making sure that we have connectivity, so that when Industry 4 really becomes a useful thing, we will already be collecting the data, we'll already have connectivity to machines, and we'll be able to close the loop. And really, that leads on to our fact that we are engineering-led at the beginning in terms of our design for additive, but also at the end of the process, we have the full quality systems in place so that we can deliver finished, qualified parts from powder right the way through to product. And so we have, and you'll see the full CMM inspection downstairs, and that allows us to be able to provide PPAP quality systems for automotive and aerospace, which is really important if you're going to start providing or supplying into production. So that's an introduction into the DMC, and you'll see a lot more later, ask lots of questions. So if you haven't met already, Nigel's the COO of the DMC here, and you'll be also introduced to other members of the team. Key members are people like Stuart Banyard from an applications point of view, and Thomas, and then Matt, who's a metallurgist. But we'll introduce you to all people who go around, and please ask as many questions as you want. So, on that note, if we introduce James,
if you
want me to do,
James,
I'll introduce James. So James, you're going to be talking about voxeljet or enable today. So James from voxeljet is going to talk to you about polymer, Additive.
Well, that's additive.
Perfect.
Less about voxeljet.
Okay.
mention your
so gifts give away. People can pass this around, take one, help yourself. These are little keyring bottle openers that are manufactured in titanium on our Renishaw machines, and they've got a little STC logo on them and a DMC logo to remind you where you've been. But they're very useful. I've had one of my keyring for a long time. It's opened a lot of bottles of beer. I hope there's enough. And if anyone doesn't get one, just shout and we'll sort you out.
How long will it take?
To print one, yeah, we could probably do it. It's the post-processing that takes a long time. Thanks, James.
No problem. Thanks. Hi, everybody. So I'm going to hopefully debattle the 3D printing market a little bit for you. I can't educate you on every process and every pros and cons, but hopefully give you an overview of where the market is, where it's going, so you can work out whether it's the right solution for what you're looking at. So I'm going to give you a really quick intro, a little bit about voxeljet, a little bit about what I deem as 3D printing or additive manufacturing. I'm going to bust a bit of the hype because this is a real hype-driven market. So I'm going to break apart some of those. I'm going to look at the printing processes that are out there. This isn't just voxeljet focused. This is a broad spectrum across the industry. And then talk about when you should use it and perhaps when you shouldn't. And then what might happen in the market in the future. I'm not a fortune teller, but I have some foresight, hopefully. So a little bit about voxeljet. Voxeljet is a 20-year-old company. So for 3D printing machine manufacturer, it's quite well established, quite old. Been in the market quite a while. We're on NASDAQ listed, so we're global. We have over 300 patents around 3D printing. We split the company into two main divisions. One is services, so printing parts on demand for people. And one is the machines. So we design and build our own machines, and we use those in our factories to print parts for people. Our headquarters is near Munich, in a place called Friedberg. That's where all R&D machine building and everything goes in on this site here. And then we have quite large facilities in North America and China to print parts for people. These are our range of machines. It's very industrial. We do not make a desktop machine. I think the small one's about 250 kilograms on that. So they're all big machines. We're very well known for our big 4000, which is 12 tons in one go. But our biggest seller is the 1000, because we get most materials on that. Our highest output is actually the 1300X. I didn't name it, don't blame me. That's producing parts, one layer takes 5 seconds. That's in the production line, produces 500,000 components a year in the automotive sector. We've recently signed a deal with GE to make massive wind turbine hubs. And that printer isn't big enough, so we're going to make a printer which is 8 meters by 6 meters XY with a meter depth. So these are massive, massive machines. I think that's 63 tons print in one go, something crazy like that. Our original technology was around sand printing, actually. So we put layer sand down, we go across with inkjet print head and print glue the sand together, we ship the sand to a foundry, and then they cast the metal part, which gives you all the benefits of metal casting, and that you can do literally any metal. So this is magnesium, you can't print it, but you can cast it. Pretty much any metal, any size. We then developed binder jetting for polymers, which is used for investment casting. So if you want finer detail for the surface finish, then you can go to investment casting, which is like this part. So you pass that round as well. That's an aluminium. And then more recently, and what I'm looking after now is a new division for polymer sintering, which is plastic components. I don't have the big parts here. We can print up to 1 meter. So we can pass a couple of those around. But I'm not here to pitch about voxeljet. Oh, just so you know, if you're not a foundry, it's quite hard to use the printing technology. So our partner in the UK is Enable, and Enable have a partnership with DMC. So you can access this technology for casting sort of any metal, any size through either Kieron or myself. So 3D printing, what is it? So you can start off here. This is, I did a quick Google search, the cheapest 3D printer I could find at the moment, £137. You want to get into 3D printing, go and grab that printer, £137. Whether you'll actually get a part that looks like what your CAD file looks like is debatable. But if you're a tweaker and you like something to play with and you can get it right, then a lot of people start there, and it can be quite a lot of fun if you have a few millennia to spare tweaking it. Or you can go right to the top end, and you spend a few £1 million on a big machine like this with 12 lasers shooting around, sintering metal all over. Again, you can't just plug and play these sort of things. You have to be an expert in either of these really to get them working properly. But that is the scope from anything from hobbyists up to the big industrial bits of equipment. And 3D printing or additive manufacturing, loads of people debate what's what. Doesn't really matter. For me, they're both the same. It's adding material. You add material, whether you do it with a print head or with a laser, whatever. Additive manufacturing for me is adding material where you need it. There are over 100 different processes, so I will talk through some of those later. And the main benefit is that you can make more complex parts and you don't need tooling. And each part can be different, which is increasingly important. So calling out the hype, as I said earlier, this sector is full of hype. Some of the marketing budgets are bigger than the R&D budgets. So you've got to kind of work out what's true. So HP's in the market. They've been in the market for a while. So they obviously do 2D printers. They also do 3D printers for both metal and polymers. And you can see some of their headlines. They're accelerating mass production with 3D printing. Another one here with a collaboration with Volkswagen. So this is about their ID3 launch event, and it's serial production of 3D printed metal parts, 10,000 high quality parts produced. What is the part? Can you imagine? Come in. Oh, excuse me when I press the wrong button. It's that marketing piece. If you look at that surface quality in the detail, I don't think that's a high quality part. It's not a production part, it's a marketing giveaway. It's not as good as Kieron Salter, to be honest. It's got less use. So it's a little bit more hype than I'm happy with. But hey, they've got to do their marketing somehow. BMW did a better job, in my view. This part here, fully optimized for 3D printing, quite difficult to make. I wouldn't say impossible to make, quite difficult to make other ways. Went on a real car, their i8, this is the bracket on the flippy lid bit. So they did make real parts on real cars. But there was big hype around serial additive manufacturing, industrial scale 3D printing. How many are they making? 3,400 a year. Not really huge, is it? It's good, but it's not, could be better. So there's hype. It's all over the place. So kind of what I'm saying is, don't believe it all. There are real production things out there, but they're quite hard to find. And Kieron is pushing that forward. And there are companies that are pushing forward and doing it in the proper way. With the quality standards, being open and honest about what is achievable, what isn't achievable. You've got to really hunt those out at the moment, unfortunately. So some things need to change. Let's talk about it a bit. So what is additive in my view? Additive is just another one of the main forms of manufacturing, and all of them have been around for millennia. Okay, you've got forming, casting, molding, all that sort of stuff, like pot making. You've got subtractive, got taking materials away. Somebody made a dugout canoe millions of years ago. And additive, laying bricks out to build a house. You're putting material where you need it, right? That's like binder jetting. So for me, it's just another form of manufacturing, and there's lots of processes within each of those forms. The thing about additive is actually maybe it's not advanced technology because it's about 2 centuries later than all the others got mechanized. But what's important here is there's, like with the other processes, additive is just a high level sort of category, and there's lots of other processes within that. And if you're going to understand whether your part should be made with additive, you've got to start to understand the different processes and know which ones are most suitable for you. And that's not easy, to be fair. let's have a look at the main categories. So over this end, sorry it's a bit small because there's lots to get. I didn't draw this, this is taken so much easier. Fat polymerization, so starting with a resin basically and curing it a bit at a time. So usually with lights, so either projected lights or lasers. I've just put down the bottom what I think is kind of the king USP in each of these areas. So that sort of stuff is really good for fine details, nice smooth surface finish. Then you've got material extrusion. So this is basically a hot glue gun on an XY going around and putting material there. That's the 137-pound printer is one of those. You can get them up to aerospace grade. They are making aerospace parts of this one generally. Great material choice. You just change the temperature of the nozzle to mount different materials. So good material choice and low cost of entry into material extrusion. But material jetting, which is using a print head and jetting the material down you want through the print head. It's really good for multiple materials because you can get loads of different print heads on there with different materials coming out in the same print. So full color prints, nice, really great looking pieces. But because all the material has to go through a sort of a micron-sized hole, it takes a long time. So it's basically binder jetting. So this is mainly where voxeljet is. So layer of powder, printed glue on top. You can do that with loads of materials. The main benefit here is because the print head, our biggest print head at the moment is 1 meter wide. We're about to make a 3 meter wide print head, and that zooms across the layer and just binds it really, really quickly. So the productivity of these machines is massive. Material choice is currently fairly limited, but if you use it like we do, and I would say this because I'm from voxeljet, if you print a sand mold, you can pour any metal you like into it. So you can get a range of materials. Powder bed fusion is probably the most common one that you'll come across for high quality parts. This is a layer of powder down and then sintering it with a laser. Loads of materials, polymers, metals, all available there. Hyper quality because you can get the most consistent material quality in that process. Direct energy deposition is pretty much like welding type techniques, but on a robot. These are good for really huge parts because you can just get a massive robot. And then down the end, there's what's called LOM, which is very niche, as I put there. For laminating PET, they're basically laminate and cut at the same time. So you can laminate a layer and cut it out of paper or carbon composite and build up your layers that way. So quick overview. And this is the landscape of all these different processes and suppliers in here. Okay, this is why people might say I'm an expert, but I'm not, because there's too much for me to understand. Okay, so what we've got broken down here is you've got different materials, then you've got the general process time, then there's subtypes, and then there's machine suppliers, and each machine supplier has a range of machines. So there's thousands of different machines out there. So if you had a 3D printed part and it wasn't good, doesn't mean 3D printing or additive isn't good. It means that the process used, the material used wasn't good. There most likely is a solution out there for every part. Maybe it's not the right solution because maybe subtractive or forming or some other manufacturing process may be better. But always consider the process being used, the material being used, the supplier. Even I haven't even mentioned suppliers because the suppliers are the next level over here, and you have different grades of supply. You know, you have the small thread in the shed up to places like this. So it's a real complex market. Don't lump it all together. Really start to do your research and speak to experts to try and understand whether additive is the right solution for you. So when to use it, I regularly say this, even coming from 3D printing, if you can make it in a traditional way, you probably should make it that way because those processes have been refined over a lot longer than additive. But there are reasons why you should use additive as well. So let's go through a few of those. Complexity. So I bought some parts because everybody loves parts. That somebody may be able to prove me wrong, but I don't think you can make this any other way. So when you have a complex part, when you can add value through design, when there's something about the complexity of the part that makes it really difficult, it's not impossible to make a different way, that's when look to additive. That's aluminium. Part consolidation, the other part that went around was taken from basically a fabricated method with sheet metal, then joined together, optimized, take weight out, and put together in one part. So it can save weight, it can save cost. So when you're putting lots of parts together, that's when you can save. So when you're looking at an assembly of things, and how to make that part, how to make that part, the first question you ask is, do they need to be separate? Can I actually put them together? And if I did that and made it with additive, does that save cost? Does that improve performance? Does it save weight? Something like that. Lead time is often the driver for 3D printing. and that's mainly around the prototyping and stuff like that. But there's other ways that it can reduce lead time. Obviously, tooling can eliminate the tooling, so that's the main fast bit about additive is you don't need tooling, so you can get manufacturing straight away. Faster prototypes, I'll talk about a little bit more on the next slide actually, but you can iterate much quicker because there's no tooling, there's shorter lead times, you can iterate your designs a lot quicker and improve on those. Pre-production ramp up, this is something we see at voxeljet quite a lot. Before people commit to tooling, they can manufacture the product with additive, get it in the hands of customers, start to get feedback from the market, start to understand how many parts they're going to need to manufacture, especially for the last few years with Brexit, with COVID, with Suez Canal. People don't know how many products they're actually going to sell. So the old sort of calculation around tooling is quite a difficult one for many companies. So actually you can get production level parts in the hands of customers and really get that market feedback before you invest in your tooling. You push your tooling investment right back to product launch. So any tweaks and changes you want to make right at the last stage. And it makes product launches quicker because you can iterate so much faster. So they're good reasons to use additive. Other good reasons is batch sizes. So I should pass this pen around. Another example from Enable. Enable made 48 of these pens, every one different in one batch. Everything different. So they tested all the mechanisms, the design, features, and stuff on it. So they made that within a couple of weeks, I think. So you're increasingly getting this where mass customization is coming in, where you want a short number of parts per variant, but the overall design may stay the same. So batch sizes are one in mass production, basically. Process savings, so obviously no tooling costs, as I've already mentioned. If you're part consolidating, it's reduced assembly costs, but 3D printing is also getting used a lot for jigs and fixtures and tooling on production lines. And that can save and improve productivity on this production line. So there can be quite significant process savings in there and material cost savings often as well. And last but not least, marketing. So this Adidas shoe here, 4D shoe, it's been shown that if Adidas put this on the shelf next to all the other shoes, they hardly sell any of them because they're quite expensive. If Adidas put it on the plinth and say it's 3D printed, they sell loads of them. So it's a massive marketing thing. And a lot of companies have been using additive as a marketing tool. So it shouldn't be forgotten because it has value there, obviously. Oh. So let's look at what I think is going to happen in the future. Please don't look at where the costs are, just view them on there. I'm not saying these particular processes are awful or anything, but what I'm saying is there's too many processes out there and there's too many companies. So that's going to have to change. It's too confusing for the market. There's not enough opportunity for everybody. So some processes will fail. They won't find their niche. They won't find their applications. There is already mergers and acquisitions happening. There's a few big companies that just IPO and they're just buying up their competitors basically. So that is happening. And then there'll be standardization around these processes. So you'll know you can get the same type, same standard from each company, each machine. That doesn't exist at the moment. So that will happen. The market will get easier from that standpoint, but what's going to get more difficult is patent applications. If you look at the patent filings at the moment, sort of last 20 years have been about machine and hardware. The last 5 years and onwards is about applications. So people are filing applications around using additive for particular purposes, and this might start blocking you guys from using it. So this is going to make it even more complex. There's loads and loads of patents going in the automotive sector using additive to enhance performance in X, Y, Z, and around electric motors and all sorts of stuff. There's consumer goods patents coming in, a lot of stuff around eyewear, insoles, midsoles, stuff like that. So the market from this perspective may get more complicated. So good luck. Supply chain development. What's going to happen? So what I'm seeing from voxeljet is a lot of bespoke solutions. So voxeljet is moving more towards this level. I mentioned our GE project. It's another project we put into an automotive production line with a big printer, the fast printer I mentioned, 500,000 components, all the same, coming off this line every year. So more bespoke production solutions, either volume throughput or size of part or some other specialism. There are becoming more AM specialists like the DMC who are going to be probably process agnostic and really understand the benefits relative of which process is going to be best. And these are going to be like your machining company or your forming company, or they're going to be another way of making parts and going to be your experts to turn to when you need help. But you also start to get it going into existing supply chains, so existing machining companies getting additive as well. So we'll see that happening more in the market, I believe. And hopefully that was a bit of an overview for you and see how the market is. Are there any questions?
No questions.
Excellent timing, mate.
Yeah, just going to pick up on a couple of things that you said there, James. So the complexity of the market and the machines and choices that you've had parts made, and you've gone to somebody with a part and to make one of those using the recent technology. You've had failures, which probably is because it's the wrong material, or the wrong machine, or the wrong supplier. And that's one of the problems that we're trying to address here, actually, at the DMC, which is the first contact with an engineer who understands that landscape and can point you in the right direction. And that's something that's missing in the market. If you go for a print bureau, you won't get that service. And very often, the answer might well be, as you said, AM is not the solution. Use a traditional process like casting or CNC machining. And sort of the anti-hype to the hype, we are doing what we consider to be large volumes of production parts, but it may not be at Volkswagen level. So if you look at some of the parts we're showing downstairs on the Murray project, for example, where there's volumes of 500 cars, it starts to make sense. When you start to eliminate tooling, suddenly the business case starts to add up. And an example on the Gordon Murray car is that we might be making a fan house and 500 units, but cable clips and pipe clips and other little bits you just don't see or don't notice in the car. We're making up into 250,000 parts. And the advantage is that every single one of those 250,000 parts could be different if it needed to be. Worst case, it's not. So, thank you, James. No questions on that. And another point that James made there about partnerships, and the DMC is built collaboration partnerships, and Enable is one, Laser ones others, Finisher others. So if you've got ideas of how you want to collaborate with the DMC, not just be a customer, then we can do that too. So next presentation is Dr. Fernando Murguia.
Yeah, that's
Brilliant.
I get it all the time.
Who's from the Warwick Manufacturing Group, who's going to talk about creating value throughout manufacturing.
Thank you. Good morning, everyone. So yeah, I work with the Warwick Manufacturing Group, specifically with the SME group, which supports SME companies, and we help them to develop their products and find ways to bring value to the company through manufacturing processes. Well, as James has just mentioned, for example, adding value in the manufacturing context, I mean, we can talk about like different value propositions, but specifically what we do, just to have a context, is material assessment, processing, manufacturing optimization, simulation, product design. I mean, all the product development side from creating a product, where we are specifically helping companies with even the life cycle process and sustainability. And that's a big, I mean, specifically, what I do in this group is CAD simulation, prototyping, additive layer manufacturing. We're starting to look into hybrid processes as well, human-centered design, and all of this translates into creating prototypes and help companies develop all of their strategies. We also have these other areas, I mean, metals, polymers, and materials, ceramics, surface engineering. But I mean, for now, I'll just talk about the additive side, which is like the how can we bring value to these sites. And well, we also have supply chain networking, consulting in all of these areas, and funding. And well, some of the companies that we work with. So yes, as James just had mentioned, there are several technologies that can be applied depending on what are you looking for. If you're looking to develop a product just for design review, if you're looking for an end part use, if you're looking for a performance part, depending on if it's a high volume or a small volume of a batch, there are different technologies to be used. So I mean, obviously these are just some of them, some of the ones we have at Warwick Manufacturing Group. And I mean, as we have seen, I mean, depending on the end use is the one that you will apply, and the process is very, very important to figure out what you're looking for. I mean, if you're looking for end use parts, probably you won't be using stereolithography because I mean it's only for like volume and details, but not necessarily you will be having a performance part, or you can be producing just small batches of those prototypes. So it's very important to see how the workflow will go. Only like looking at the materials, the process, how are you going to build, for example, this is a fishbone graph about the FDM parts. I mean, all the different areas you have to look at. I mean, surface, dimensions, build time, post-processing is very important as well, because you can probably print all your parts, but the post-process will take you even like longer, depending on the volume, if you want to have this last, depending on what's your end use for the part. So for example, talking about the process, it's very important to.
Can I jump in very quickly?
Sure.
People at home can't see anything. So 1 second,
It's
please.
very important to determine how exactly you're going, which technology you're going to use first, which material are you going to use as well, and you start building up how your end use part is going to be relevant. I mean, for example, this is just a chart of different materials that can go into the 3D printing part, but obviously you have costs, you have strengths, you have different aspects of it, and probably if you're looking for a specific material, that automatically discards some of the technologies and some of the printing processes. So according to the roadmap, you automatically start to select what is a proper workflow to follow. So yeah, for example, to be more concrete in some of the projects that we have worked with and getting the technical side, aside. For example, this is a project for a company that, for example, they were still in the grills and the barbecue grill business, and they were looking to diversify. So they came up with a nozzle that can pour the sauce in glass bottles by itself, by pumping the sauce out. And obviously they had the concept, but they didn't really have the means to do their prototyping and to test everything. So we just started by building up mock-ups with different technologies from an FDM, which is from the PolyJet machines, which can give you a sure level of softness in the material, to even TPU, which is way up to the spec. But we wanted to test how the material will feel into the concept. Here we can see that you have a certain level of shore in the material. And we started looking at all the solutions that we could find with several iterations to see how the engineering of the product would be successful. And in the end, they ended up doing this product, which, I mean, they're selling thousands of parts of it. They even are changing the focusing of their business because they are now into the pumps for the sauces more than the grills for barbecues. And I mean, this is just an example of how the design review and the usability and the manufacturing feasibility can bring value from the additive manufacturing side. They were not looking to go that strong in this sense until they started looking at the additive side. And they can actually, I mean, we're able to take informed decisions by looking at the feasibility of the product. Actually, this enabled them to start producing all of this. So it was very valuable to bring all these kind of prototypings, and they ended up doing it with natural rubber, which is a more sustainable side of the polymers. And even though we're not able to print in these natural rubbers, there was a very close approximation to how the product will feel and work. So yeah, I mean, this is a very successful case where from nothing they built something very successful. Another example is the camera back company, where they were looking for the USP that was not using Velcro for the divisions inside the cameras. So you basically can change the size of the divisions by using some kind of clips. And yet again, by doing several iterations and looking at the geometries and usability, we were able to come up with another concept where you can see, for example, they were using this kind of Reeves to hook up to the walls of the bag. And then we ended up doing a complete different mechanism, like for example, those pens that you can click in, click out. Just hooking it up to the design. And well, that was supposed to be an animation, but yeah. I mean, that's just like an assembly. But I mean, as you can see from just the read, we were able to come up with another complete different mechanism. And the value of this is that this even enabled them to look forward into a new manufacturing process where they were looking even to automation, to robotic arms, to bind all these ribs to the fabric of the bags. And I mean, what we were able to do with this additive manufacturing process is for them to go even further for what they thought they could be using in their products. And even, I mean, the product from automation was very successful. They installed like a new kind of section where they can bind all of these parts to the fabrics. And yeah, for example, this is another project about a chemical tank, which needed to use very strong chemicals inside, like sulfuric acid, things like that. I mean, this was just a proof of principle. It was a very difficult print. I mean, that's like the most challenging part of it, because as most of you know, I mean, you have the support to take half of the final part. But when we succeed to do this, we were able to translate that technology to the actual chiller. And I mean, this reduce the time to market of their part of their actual product significantly, like, I mean, dramatically, because they were able to test this in the lab. And actually this was using an FDM, which is an industrial size 3D printer. And yeah, I mean, in the end, the thing that I want to convey is that the time cost and time to market can be significantly reduced by applying these technologies. Even though they didn't know the exact know-how, which way to go, which material and which technology, just by digging up on the workflow, we were able to succeed with this one as well. In this case, I mean, this is an electric scooter. The company was reverse engineering some other products, and they were looking to secure some budgets and fundings to the products, and they came to us. I mean, we were able to produce all the exterior parts, redesigning most of them. And in the end, they were able to even secure more budget than the one they were thinking of, just because they were able to show that to their investors, and they were delighted by the results. And this is some of the aspects that additive manufacturing can bring to the company as well. I mean, it's not only your product development process, but also the other sides that it can affect to improve the operativity of the company. I mean, this was a very strong case about how they were able to secure these investments. and it was just all about the additive side, which they were even considering to produce the first batch, all in additive, obviously with several iterations, making it more optimizing the parts. But it is a very good case for securing budgets, for example. And these are the first parts we built. And yeah, I mean, it was very successful for them in that side. This is another project we worked with. These are like the tire bikes that you can find in London, for example. And through additive, we were able to, again, make the company, enable the company to secure budget in a very significant kind of like cutting time. And yeah, I mean, in the end, we worked with them for over a year, but the size of the project was enormous. I mean, they're still growing in their tire business of bicycles, but we were able to develop all these 3D printing parts for them to and show the know-how to the business on how to invest in these technologies for their product development and R&D. And yeah, I mean, finally, what I can take out of this is like the printing technology is very important, as James was mentioning as well. Material selection as well. And all of this will give you like the end use and the gateway, as you can optimize the whole process in the product development side, in the design review, prototyping, and this can significantly bring you to the market in ways that, I mean, sometimes the customers don't even think that we can make these targets, but I mean, in the end, it's just like proof of that this can significantly improve all of this. But yeah, that's it. Any questions?
I have one initial question. How does a company access the Warwick Manufacturing? Is it totally customer funded, part funded?
Yeah, in fact, you first have to qualify as an SME, be within region, which we used to be only in the Midlands, but now we're expanding even to Cambridge and all of the east of England and more to the south. Then you have to apply for an engagement form. I mean, it's very easy. You just have to contact us, and if you qualify with all of these points, you're able to have support from us. There are different engagement levels. I mean, it can be just like an engagement from support of a week, because maybe you need to know that which additive technology would suit best your product or your product development process. Or it can even be an internship, or it can even be a long-term collaboration. I mean, it all depends on the scope and but I mean, it's just constantly contacting us, and we have all these funding options and levels of engagement. Yeah.
Another follow-up question that yourself and also James might have some input here is, how do we make it easier for people to adopt, to engage? I don't disagree with anything you guys have said. It can be a really complicated landscape. We deem ourselves as experts, especially a drip under pressure and XDL quantities. How do we make that road to adoption easier for somebody coming in from the outside? Questions open to both.
Well, first, I mean, that's why I put some emphasis on that, because first you need to know what's your end use for your parts. I mean, if it's going to be only helpful for the product development side, or if it's going to be an end use part, how many you want to produce. Maybe it's just a step to get into another way of manufacturing it, but you have the prototypes and I mean, it's all about showing them which are the options, which are the ways to go into it. And I mean, it really depends on the product, really, because I mean, it's so different from one to another that, I mean, it's just like case studies, and you have to find out which way to go, but
And so we need a trade association. Trade association that can be obviously completely agnostic to materials and processes, that help put together design for manufacturing courses with colleges and universities, and start to run events, seminars. The DMC doing STCs, doing it locally. So, but it needs to be an industry-wide thing. And the problem is, all of us at the moment are just promoting our own processes and materials, and we need to be a bit more open about actually when ours makes sense, and actually saying go and speak to somebody else because their technology is better. I think that we've been hurt quite a lot by the hype, so I always try and call it out. And people throw CAD files at, can you print this? And you look at it and go, no, injection mold it because the tool's going to cost you £1,000, right? It's just, we need to just actually, as an industry, be a bit more open and honest, and also invest in education.
Genuinely, the answer to your question is come to DMC.
We are technology agnostic, material agnostic, and sector agnostic, and the whole reason for us establishing this facility and being engineering led is to answer that question, which is where do you go to get the right advice? Not just to send you that particular solution, because that's the machine I've got and I want to put parts on it. And that's where we've been in the industry. And the industry's thrown up out of prototyping and model making. And we want to make a step change and go back to basics and say what problems we're trying to solve, the application, find the right solution. And as I said, we're quite happy to say the answer to your problem is to go back to CNC machining. And we'll probably help with that, but that's we're not here to decide if manufacturing. And that's why it's very important to have an able on board so that we've got that active casting, because there's a sweet spot for active casting that active manufacturing doesn't fit. And we don't want to try and we try and force customers to say additive's the answer to everything. They'll be disappointed. So genuinely, I do think places like the DMC, and I'm happy that we can copy what we're doing and do more of it, because we need an industry, not just one supplier in the supply chain. And whether it's a great organisation that helps into it or not, I don't know, but I think we just need to become more mainstream actually, and that's why we joined up with MedUK, for example, is to, the industry needs to know about manufacturing as a tool in the toolbox, not as a special thing that people don't understand. That's some sort of needs to become mainstream.
It's incredible how many people still don't know what additive manufacturing can do.
Yeah, and the hype, busting the hype is actually a lot of people think printing guns or making stuff in your garage. You've got 3D printed, you can make anything you want, that's the hype. That's not true. And we also need to get away from this kind of model making, rapid prototyping background that it's had. And the two things for me that have changed dramatically in the last 20 or so years since I've been using Additive is software that we have to design stuff. It's obviously changed a lot. I mean, our first 3D printing component was a wind tunnel model for a full conveyor touring car. It always comes up, doesn't it? The full conveyor touring car had a long part which was made out of 3D printed, the 2D paper stacking technology, but we didn't have 3D CAD system then. I don't know how we made it, but we did. I think it was called the PPS system that designed it. But the software's changed, not just the design, but also for running the machines, and also materials have changed. We're now able to make low volume parts, which we call prototypes because they're one-off, so they're part of the development iteration, that are out of materials that are almost like the life of the finished product, which we couldn't do before. It was stereolithography part that was maybe a good geometric representation or allowed you to do some physical work, but it wasn't a product representation. So those two things have changed a lot, but it also means you need to now understand about materials. So you need to have an intelligence. You need to have all the CAD software and all the systems to run it. And so it's quite a complex landscape. Thank you, Fernando. So do you need to prepare a presentation again whilst you're doing that? Shall I do a dance?
Yes, please. Well, or introduce Laura.
So Laura Gonzalez is going to talk to us next. And a nice segue from land transport with scooters and bikes to space. And you're going to talk about active manufacturing in space or active manufacturing in space.
Exactly, yeah. I mean, I could have thought going to space.
It's my aspiration, by the way, to have a DMC factory in space. I wouldn't say you heard it yet, but I've said it a few times, but genuinely, that's what we're doing.
Yeah, exactly. It's one of the topics we're thinking about. a little bit here. I think, yeah, thank you for the presentations before as well. It's been really good to like see the overview. And my name is Laura, Systems Engineer at the Catapult, and I'm working, yeah, with the Catapult for 1 year. But before, I had some background in space. I studied aerospace engineering and masters, and also worked in a few space missions with the European Space Agency. But my passion has always been manufacturing, so I'm very lucky now at Catapult because I can merge both things, manufacturing and space. And yeah, back at university, I did my first 3D printer, was actually very similar to the one that you said it was the cheapest in the market. So I started with FDM, putting it together myself, and I've gone through all the rapid prototyping, a little bit of type, the maker movement, digital fabrication, and now I'm using it in a more professional way. Let's say in the Catapult, where we have a 420 by 420 metal additive manufacturing system. And yeah, it reminds me back of my times, and also like my master's thesis, my bachelor thesis, and working in the university with the fabrication department with a very small powder-based system. But it was only this for a huge machine. We could only manufacture something like this big. And now, you know, the one that we have is way bigger, and we're literally building rockets there. So it's been a long way. I mean, yeah, so let's dig into it. Yeah, just a quick raise of hands. I think, yeah, we're getting closer to the break, so I don't want to take too long. So who has already heard about the satellite applications Catapult before? Okay, good. So we can go quick, and yeah, just a little bit of background. But our mission is to empower, innovate for a better world, but empowered by satellites, by space. We're a non-for-profit independent organization. The Catapult is actually one of the 9 catapults there in the UK. They were set up by the government to energize and to innovate in some specific strategic sectors. So there's catapults in the energy, there's catapults in renewable energies, health, in different sectors. And our catapult is the one focused on space. Our aim is to grow the UK space ecosystem, and we do this by energizing the market, empowering technology, and enabling business. So, for example, we energize the market with finding new markets, new opportunities for small companies. We work with both large and small companies, but mostly SMEs, so that we can support them and help them grow. And we do this also through technology. We have lots of technical experts in the Catapult, and we help them with some, for example, IoT in orbit service, in orbit demonstration programs, in which they can come with their experiments, and we help them put them in space. And we have some small satellites, because the space industry has gone through a really revolution in the last 10 years. And now it's not only about big satellites or big corporations or governments, but it's actually about smaller satellites, like a microwave size, more or less. You can put anything you want on it. So we're helping a lot in that technology part, and also through enabling the business. So I think, yeah, one of the strongest things about the Catapult is that it has this network and connections to all the industry, but also with academia. So we help with that bridge between industry and academia, and help them grow and connect the dots. So sometimes it's not in our services, but it's us pointing them to where they need. Very similar to, yeah, we were talking before, right? Like about this collaboration that is so needed. We have our headquarters in Harwell, but we have some new facilities in Westwood. That is where we have this manufacturing for space equipment and facilities. And we work very closely with the LEP, the Hampshire Local Enterprise Partnership, and that's where we're developing these facilities. But we also work regionally, and we have regional teams that help focus the space and enable these businesses not only in the Oxfordshire and Harwell and Westwood, but actually UK-wide. And yeah, so satellite applications Catapult is being focused mainly in the satellite applications. We call it the downstream part of the space. So Earth observation, navigation, all the applications that space and satellites can do towards us on Earth. But now we're looking more also towards the upstream. So it's always been divided between downstream and upstream. And now we're working with different launch companies around the UK. We're helping setting up spaceports. Like some of you might know that next summer, there's going to be the first UK launch from Cornwall. So it's going to be a horizontal launch with Virgin Orbit, but there's also some other initiatives up in Scotland with Sutherland. So we went and visited there and helped a little bit, and some other facilities like the ground stations we have in Downhilly, or the mission operation room that we have in Harwell, where Astroscale, for example, is operating LSD, one of the missions for the removal. And in between there's this new part of the space, not downstream, not upstream, but in orbit. So we're looking already to these concepts that might seem a little bit futuristic sometimes, right? About space-based solar power. So basically putting big solar panels in space, beaming the energy down to Earth, because it's actually more efficient that way. Or things like in-orbit service and manufacturing. So yeah, super futuristic, but it's actually already happening. Yeah, it is happening. The strange phases that this is something we're already working on. Companies are doing these things already. And other things like, for example, microgravity commercialization. And just a quick example of something that might be of interest to some of you here is this microgravity commercialization is a market stimulating program that we have for advanced materials and manufacturing. So showing the manufacturing industry and the advanced material industry the benefits of manufacturing things in space. So we're working with the European Space Agency to do this and to highlight what the benefits are, because you have microgravity, you have vacuum, and there's actually already some demonstrated use cases, like producing the carbon optic fiber that is actually better in space, but it doesn't have so many defects. So there's already some development in this area, and there's some examples. You can check their website already there. And we do this by getting a lot of partners together, not only in the UK, but actually internationally and in ESA, I mean, around all the member states of the European Space Agency. And yeah, these were the super futuristic concepts that someone was putting weird faces around. And this is actually like already happening. So we already have debris removal. There's Astroscale, like a company that is based in the UK as well, removing debris, removing all satellites from space and getting them to burn in the atmosphere. There's already lots of inspection being done, but there's also other things that are going to be in the future. So refueling, we've been looking last week at some refueling ports, because once you have your asset in space, you might want to put some more fuel and put it up and like extend the life a little bit more. Also some human exploration assistance that probably is going to be longer in the future, like long term, but also some assembling. So to do these solar powered based structures, we need to be able to assemble very large structures in space or to manufacture in space. So that's where, yeah, in space manufacturing comes along, because you're not going to be able to fit all of this in a rocket because you have fairing limitations. But if you can assemble it or manufacture it in space, then you have so many more opportunities to operate in space, not only in orbit, but also when we talk about going to the moon, Mars, or even the asteroids. You could go there, get some resources and utilize them in a different way. So all this manufacturing expertise that we have on Earth is actually very important that we translate it to space and that we have this cross-sector collaboration. So that's, we're super keen to engage with all of you in any ideas that you might have of some processes that you already are developing that could be actually exported and exploited somewhere else. Because the other focus of the Catapult is not only about research. We actually don't really like science and research so much. It's more about commercialization and making it commercially viable and get some revenues out of it for the companies, not for us because we're not for profit, but it's to energize this ecosystem and get some companies that can get revenue out of it, and we create this demand. So it's not only supported by the governments and the agencies anymore, but there's actually this activity in space. We've been around IOSM, especially doing some research and learning what's it like in the market. We put together this report for the UK Space Agency, and we found a lot of things in between them that the UK is very well placed. We have all the technology, or almost all the technology that we need in order to be successful in this market of in-orbit servicing and manufacturing. The manufacturing part is always a little bit later on because we need those building blocks first around close proximity operations and so on. One of the things that we found was that we were lacking facilities to be able to develop and test these things in Earth before we send it up. So we're actually already actioning that and building a new facility in Westcott together with the lab, Woodhamster lab, to do these things. So inside here is going to be the metal additive manufacturing system that we have temporarily in another facility, but also we will have some close proximity operations tested. And these are just some pictures from the last weeks, because it's been like the building is going up very, very quickly, and I could find them. So it was just to show you, it's almost ready. It should be ready by March, but then we have to do all the fitting of their robots and the machines. But this is more or less what we want to replicate. So it's a proximity operation simulator. This is the one we have in the DLR in Germany, but there's nothing in the UK, and we've been told that it's very difficult to access this one. So once we found this out, and all the industry was asking for it, so we put it together, we're designing it, and we will hopefully have it ready by summer next year. This is the other building that I was telling you about. This one is ready already. Nigel's been there sometimes already. And we have some manufacturing, we call it manufacturing for space, manufacturing capabilities. We have the metal fab, the additive manufacturing system from Additive Industries is 420 by 420 by 400. There's powder-based with lasers that we were mentioning before. But we also have a CMM, we have a liquid crystal printer, the normal maker, a firearm for the measurements, water jet cutter, different manufacturing equipment so that we can help companies around the site. Because the site is actually Wasco. I don't know if you're familiar with what is it. It's between Aylesbury and Bicester, and it's been a lot of history about rocket development there. So after World War II, lots of German scientists went to the US, but the ones that came to the UK were actually based there. It was kind of secret until not so long ago. And there's some plans and some documents that we found here that date from 1947, and but then all the way through. So in 1950s, the study sign that is from the 1950s. In the 2000s, we already had some companies testing rockets there. So we have Urban Engineering, NAMO that is still testing. And now we have the UK Space Agency National Testing Facility just open over there. So it's great for us also testing. So the idea is that all these companies could help, we could help them manufacture the things, and then they could quickly test them in the same site, maybe come back for an iteration and go and test again. So we're building this ecosystem over there, and we want all of you also to be involved in this ecosystem, because it's not so far away, to be honest. So this is in the 2020s. Last year, this is Protolons. It's actually one of the companies that we incubated in the Westcott Incubation Center in Catapult. Because apart from the innovation center that use the water machines now, and the one that we're building, we also have another building that we do incubation for companies that do electric propulsion, chemical propulsion, so all based around propulsion, but also any other space-related activities. And it's there in Westcott, and some of them, they were just an idea, a few university students actually from the University of Cambridge, and now they have their own company, their own test site there. They have some funding, and the idea would be that they would be building this type of rockets with us, with our additive manufacturing system. Because as they were mentioning before, there's lots of benefits for building the liquid rocket engines with additive manufacturing. So the first one would be probably the cost reduction, as you were mentioning before, but also the flexibility in the manufacturing. This is another example of launcher. I saw it actually in Formex last week. I don't know if any of you were in Formex last week. It was huge. You were saying before how many companies there are. It was my first time in Formex. I mean, I love additive manufacturing, but it was crazy. And I totally agree with your suggestion that there's so many that he's gonna, he needs to do them. But I saw this one there, and it's actually 1 meter by 400 by 400. And it was developed with a launcher that is a propulsion company together with AMCC.
AMCM.
Yes. It's supposed to be there. Sorry, the pictures came wrong. But they have this system that they developed. It's EOS group, and they developed the machine because there was no machine in the market that could build something so big. You would have the benefits of creating very complex geometries, the quickly iterations and design, and that also reduces the development cycle and the time to market. Another example that I also saw there, I don't know if you saw them, but there's a smaller company from Spain, from Valladolid. It's actually very next to my hometown in Spain. And Pangea, that is a propulsion company from Spain, they developed an air-spike engine. It's very difficult for these air-spike engines to work. So the concept has been there for ages, but because of the manufacturing processes and materials, it's never worked properly. Actually, 2 weeks ago, they fired it in VLR in Germany, and it worked like first time, and it's like a very success, not only to light one of these air-spike engines, but also to do it right at the first time. everyone was like really surprised. It's been all over the space news, and it was really cool to see it in person in Formex, because you would see like it was the burnt one, like you could see it. So yeah, it's very interesting. They developed it with the copper chrome niobium alloy developed by NASA. So as you could imagine, to be able to develop this, there's a lot of collaboration between the AM manufacturing system, company, and also the propulsion guys. I think they were developing for 1 year. They were saying that they had 1,200 little conducts inside, so impossible to manufacture any other way. And a great success story, I guess. And yeah, this is our system that we have in Westcott. You're welcome to come and see it anytime. At the moment, it's in a temporary facility, but we hope to have a bigger facility, more suitable for the machine there. For example, I've been talking to Nigel a lot, and he's been helping a lot. So yeah, this is what we have there. And our idea is to help all these little companies in Westcott to develop their own rocket engines, test them, come back to us, and we can iterate. And for manufacturing, it's very critical. There's so many things to take into account. It's not simple, but we want to make it easy for them in that sense. Yeah, well, there's a few QR codes if you wanted to know a little more about the history of Westcott or the strategic vision that the people managing the site have. And the ideas of manufacturing in space that I didn't touch much on before, but we're manufacturing things right now that could enable things to go out with these rocket engines. They're actually finished end products, because we're working with Inconel 718. They can fly, and we could manufacture antennas, we could manufacture lots of things on Earth, but we can also manufacture things in space. There's already some manufacturing in the ISS with 3D printers that are there. And the idea would be to manufacture things that could come back to Earth with better performances, like we can see with optical fiber already, but also to use in space, as we were saying, for this in-orbit economy, or to go to Moon or Mars, because at the end, it's going to be easier and cheaper instead of launching it with the cost that launching something from space, from Earth with the atmosphere has, than actually manufacturing it in space. And for even astronauts in the future to have access to their own tools that you need in that moment, and not have to wait for someone to send it to you from Earth, it's going to be very, very critical. So yeah, really happy to talk about any of this with all of you, because for us, the cross-sector collaboration is key. We think we need to, in order to enable this UK space ecosystem, we need to leverage all the technology that is already being developed around it. And we think it's a very interesting space that has a lot of benefits to each one of the technologies. So please, yeah, do contact us. In order to energize the market, enable business and power technology, we need this collaboration, and that's what the Catapult is supposed to do. So yeah, we have some collaborations already with all the catapults, like NPC, National Composite Center, High Value Manufacturing Catapults, and many other partners that we work with, Alloy, to develop powder, Proto launch all the propulsion companies on site. We're looking forward to work closer with DMC, and also any of you from the Silverstone Technology Center. Thank you very much. That's my email there. I'm going to be here until around 12. So if you need to talk, just let me know. Thank you very much. I hope it didn't go too long. Any questions?
Just one. Do you have any collaboration with schools and educational program or secondary schools?
We would love to. Yeah, I think the skills part is very critical for the Catapult. We have some collaborations more focused in universities, but in West, one of the plans is to do a skills academy. So very focused around how to prepare people and like younger generations to space jobs and manufacturing, and not only space, but all the engineering disciplines around space. But yeah, if you have any suggestion of any particular school learning program, I think we'll be really happy to learn.
And one more, so you're inviting different businesses. So depending, on us, not just for one buyer, thermal wire coating company. It's something to be beneficial for.
Yeah, definitely. Thermal coatings at the end for this application, rocket engines is very important. So yeah, you can give me your details later. Right?
So I'm talking a little bit like anything related to satellites and slide deck. So premises are our customers We've done stuff for launch vehicles. We've done waveguides that have been electrified as well. We've got components on the Mars rover now in Auto 985 and Terra on X-based material. We've got other stuff on board, catches and covers on the International Space Station as well. So not just metals, but polymers can also be used. So this in this section as well, to qualify processes, people sort of sharpen and hope that they can basically.
Definitely.
I've got a question. It's not really about additive at all. It's more about you in your slide you have the different satellites and different processes that are going to be going up into space that will be there.
Yeah.
You also have recycle. And one of the things that's obviously massive in the news at the moment, or has been talked about, is all the space debris. You know, I think there's a forecast for 30,000 satellites over the next 10 years. I mean, these, when you talked about refueling, satellites only have a limited lifespan.
Lifespan, yeah.
Yeah. But I'm interested. Is that something that we're looking at as a country? You know, Catapult Centre, are we taking advantage of our knowledge to collect the debris? Is there? I know can't be simple. You have to have clever radar, etc.
Yeah.
Is that something we're looking to do?
Yeah, exactly. That's actually one of the priorities that the Catapult has, to have a kind of net zero. We have like a whole department around it. But yeah, we are already doing from the UK and but also like around the world. And they call it active debris removal. So animations to remove this debris. Because as you were saying, the satellites have a lifespan. Usually it tended to be the geostationary satellites, the ones that are farther out. They tend to have longer lifespans, but now with this revolution in the space industry with the smaller satellites, the lifespan is really short. Like it could be 1 year, 2 years. They tend to be designed so that they can re-enter the atmosphere and burn in the atmosphere, which is it's okay from the environmental side. Or the ones that are geostationary satellites, they take them to they call it yard orbits, like it was like a cemetery of orbits that is, or they're farther away so that they are not in collision with other spacecraft, because it is a big problem, because even a little part of a satellite, when it crashes into other one, it creates what we call the Kepler syndrome, so lots and lots of debris. So I think it's the biggest issue that space has at the moment, and we are working on it. The problem is, what's the business case behind it? Because there are some companies like Astroscale that they're working on it, but they need to have some revenues as well. So it's important that the government maybe helps funding some of these missions, but also that all the companies and all their countries around the world are sustainable and they are also thinking about it. Because it was just last week, I don't know if you heard that the Russians, they were trying to knock one of their own satellites to test the technology. So like that created much more debris. So if one country is trying to clean all the space, but then other countries don't have responsible use of space, and that's when we have a problem. And that's one of the challenges of space, that there's no regulation in space, because at the end it's for all of us. So it's very important that this collaboration and international collaboration is key.
I was at Catapult a few months ago for a conference, I can't remember whether it was the annual conference or what the project was, but it was fascinating to learn about what's coming in space in terms of the industry, about to explode in terms of the industry. There was a company there, and I can't remember what it was called, but they were pitching themselves as the DHL of space. And there is a genuine business case for eventually, if you launch stuff up in space, then somebody's got to move stuff around. And so they're going to have these taxi services for moving satellites onto different orbits and moving stuff into the cemetery orbits and collecting the waste. And they will be Grundon in space collecting up the waste. And it's a huge opportunity for the UK. And I think, isn't it interesting to know that it's here at Silverstone, essentially within the cluster where the home of motorsport came from. So we've got the very best of Formula One and motorsport, as well as next SpaceX and everything else coming from this area as well. So I think it's a great place to be. And from the education point of view, if I was a kid now, want to know why I should be an engineer, build space stuff, build stuff. It's no longer untouchable, is it?
Thank you, Laura.
Thank you very much.
Have we got a networking break now?
We do have a networking break. We're actually ahead of schedule, which is unheard of. Well done, everybody. Can we reconvene at 11:15?
Yeah, so tea, coffees, orange juices, downstairs, toilets.
And then Kieron, Laura, James, and Fernando, if you could stay here for a moment.
Oh, we're in
And then
trouble.
all of you please go have a coffee. Right, let me stop the share here. So as advertised, we'll have a little bit of a break now. So I'll stop the recording, but we'll reconvene at 11:15. So we'll see you then. Thank you.
We all back up here. If anybody's not, let's carry on with that. Right, so without further ado, just introduce Matt Jones from Stratasys, who's going to talk to you about automotive applications for additive manufacturing.
Thank you. Hi, I'm Matt Jones, application engineer for Stratasys. Have the pleasure to talk to you about what we offer and what our customers currently do in the automotive spec. I'll try and keep it short. There's a lot of images, different applications, case studies and overviews, so feel free to ask me afterwards about them. A little bit of corporate stuff. So Stratasys / Object. So Stratasys bought Object many years ago. We've been around for well over 30 years. And recently you were talking about acquisitions. Stratasys decided to buy RPS for the stereolithography, which happened to have a machine downstairs. Also Origin, which is a DLP based process. And also working with ZAR, we sort of brought to market the SAF machine, which I'll touch on. Each one does a slightly different thing depending on applications, from prototyping all the way through to end use. So the previous speakers have mentioned about, materials being key. For me, it's definitely starts off with materials, the processes, application validation, and then finding the right machine that fits that need or the materials that are on offer with it. And I'll talk about them separately in a second. I'm going to start off with PolyJet, which is basically a glorified inkjet printer. Instead of ink, we use a photopolymer resin, which we deposit in droplets and then cure simultaneously as the head moves back and forth. So you can do multiple materials together, whether it's rigid, flexible, whether it's different transparencies, opaque colors, Pantone certified, biocompatible, materials with a higher HDT, heat deflection temperature for sort of very small batch testing of injection mold tools. It will never replace metal tools. The actual amount of models you get off it isn't designed to do so. For validating the design, it's more of a functional prototype as to just a visual or concept device. There's an example downstairs that we can show you, and I'll pass one around. This is a new key design. But basically trying to design a new key fob, trying to get all of the features with it. So the display, the icons, the lettering, even for example, on this one is a QR code printed on the back. You can't do it in a traditional sense. So these are actually going to be used as end-use devices for different automotive companies. It will have a protective spray put over the top that can be used. You can embed the electronics inside, but basically gives you massive cost savings and time reductions depending on the sort of customized or low batch volume of cars that this particular product is sort of aimed at. But again, as a visual mock-up or prototype, it's a really good idea. You can overlay graphics, so VRMLs. So you take the image or the graphics that you have, we can print those as well. We can do bump matte surfacing so that you'll feel the texture of the wood on there and also the fabric cover as it comes around. All done in the CAD and can be printed in one go on the machine. Next one, again, this is mass customization. So for people like Bentley, they have a specialized group called Mulliner, or for Jaguar Land Rover, they have their specialized group for the Range Rovers. You're ending up getting end-use customized parts from PolyJet. Now, PolyJet sort of inherently has really poor material performance. So what they do is, again, they overspray, they give something that gives a better stability or a UV blocker over the top. But this sort of customization with the marbling, the texture that you're getting, you can't really do that any other way apart from machining it out of marble or something else. So being able to print it and stick it in a vehicle makes a massive difference. Customizing it for the customer's needs. Not hundreds of thousands, and maybe a few thousands of these parts makes economical sense when we look at the process with the machines. This is an example from McLaren. This is again prototyping, but functional prototyping. So this is basically a boot sleeve that goes over the suspension on the car. Basically got rigid and blending through into different tool hardnesses and materials, so we can also do elastomeric. This is the software called GrabCAD, really intuitive software used for FDM, used for PolyJet, used for SAF, and it will eventually be used for the P3 once we launch that later in the year. Lots of control, so you can choose the different colors, you can choose different shore hardnesses, you can select areas on a given model. So we don't want to work with STL files. We want to work with the native CAD where we can select bodies and faces. It's also applicable for FDM where we want to increase the wall thickness or change the raster angles we put down or make more features self-supporting on holes and things like that. So really good software. You can download it and play with it. It's currently just for our technologies, but you can see here a great example of selecting the face and then changing the color or the material, the shore hardness, and blending it with different rigid materials as well. It's great end-use application. They typically last about sort of 4 weeks on the wind tunnel testing. So again, they're not sort of a couple of goes and it's failed. So 4 weeks of prototyping and actual functional testing. You wouldn't stick this on a car and rip around the track. I'm sure it wouldn't survive very long. But for prototyping, functional prototyping, it's a great example. And the next one is the automotive tail light. I'll pass that around for you as well. So this, although it's taken about 26 hours to print, this is printed all in one go. It has been post-finished and sanded back and polished to get that sort of transparency to come through. But in a traditional sense, you could do it on stereolithography, but you'd have to print each part in a different color and assemble it together afterwards, or create the molding and again assemble it together afterwards. So this is an example of printing all of the colors together in one go, full transparency, and then you can stick it on the back. So this is actually for Audi, the A3. I had no idea that each revision of a car model has a slightly different color for the brake lights and the yellows. I had no idea. It's very costly and time consuming to be able to do all this sort of tooling as well. So you can see 26 hours to print, 5 hours post finishing, and you've got to be skilled to be able to sand it back and be able to apply the lacquer. But the end result is really good, again, for prototyping visual concepts out there. There are people like BMW in China who offer a service where you can actually print in PolyJet, again with a urethane coating over the top for end use parts. So if you wanted to customize your Mini, you can do that, again, printed on the J series systems. Full color, you can change the design, they'll print it for you, they'll overmold it for you, and they'll ship it out to you, and you can fit it on your car. So common misconceptions, I mean, like myth breaking, all that sort of stuff. So yeah, PolyJet traditionally used for prototyping or functional prototypes, but depending on the application and the needs of the material, you can use it for some end use applications as shown here. Also internally inside the vehicle as well, the coating that they apply over the top meets the regulations for flame, smoke and toxicity. You don't have to worry if it gets out gases or anything along those lines. Great idea, embed the LEDs and get the light shining through. Again, mass customization for existing vehicles, or if it's classic vehicles where you can no longer get the spare parts, same thing. You can look at the design, scan it, print it. Maybe it has a particular failure mode. You could look at that and redesign the part accordingly as well. I quite like PolyJet, although it doesn't have lots of real world end uses. SAF is the next one, so our select absorption fusion technology for volume production. So this is slightly different. So it's like similar to HP machines and other powders out there, but instead of having heads that move or build trays in different directions, we move in one direction. We get much better uniformity of the heat inside the machine, so we get better accuracies, better mechanical properties as one. And there's one fluid as opposed to multiple fluids in there, so it's reducing the process down. We can do hundreds of thousands of small connections as well. Nesting density is very good compared to the cylinders out there. Applications, loads of them. So small connectors, wiring harnesses, clips, brackets, all this sort of stuff, plugs, caps. Loads of it can be done. You can do larger models as well, side mirrors, panels, and there's some examples downstairs as well. In PA12, PA11, and PP and stuff, they'll come later as the machine is released. But the H350 gives you lots of applications on the outside, but also on the inside again. So vent grills, handles, mirror covers, speaker grills, impalas as well. And again, they can all be dyed and post-finished again, the dimension. You guys have the kit here. Great example, Pantone references and colours as well, being able to fully seal a part to use it under different types of pressure, so not just atmospheric pressure as well. So SAP, great technology, lots of applications in automotive, but also you know, in electronics, consumer goods as well. So it's quite a sort of broad spectrum of applications, very diverse with the volume and the throughput you can put through the machine. Injection molding, so it makes sense, you know, if you have still large batch volumes, but not enough to invest in massive amounts of injection mold tools, it really sits in nicely, so you can reduce the lead times, reduce the cost, and get parts off a little bit quicker. You can see here nesting density and stacking the parts. We don't suffer from sort of orange peel effect or issues with large cross-sectional areas, so we can build parts flat. We don't have to angle them, which then reduces the amount of parts you can fit onto a build platform. This particular build is about 12 hours. I think in total, full build volumes, no matter what you're printing, takes 18 hours to print on the H350. So it doesn't matter what you want. You can also do half-day builds as well and take them off. Because of the temperature uniformity inside, you get really good mechanical, consistent, repeatable mechanical properties, which is where it leads into that actual end-use production parts. FDM, jigs, fixtures, prototypes, end-use parts. There are loads in FDM. It's been around a lot longer than other technologies, hence the reason this next section is rather large. I'll try not to bore you. So here's an example from Japan with mass customization of end-use bumpers in ASA. ASA is one of our best material for printing for surface quality. The battery's running low. Shut me down halfway through, you don't have to listen to me. Available in different colors, as well as you can also order customized colors if required. We can do that with material in America. But again, example here, end-use part, painted and finished. I'm sure it wouldn't pass the safety test in the UK, having spikes on and impailing people on the road. But really good material, good ink. People have tested it for centralized and decentralized strike testing down to sort of negative 40 C and up to around about 80 degrees C. ASA can also be used for low cure prepreg, so for composite layup tools as well, where you don't need to, you know, high temperatures, you don't need the high pressure stuff for consolidation and curing inside an autoclave. This is an example of a hood vent done on the F770, which you'll see one later. Thank you for buying it. Has ABS and ASA materials, so only two materials. They're typically used for prototyping, visual mock-ups. Again, because it has ASA, it can be used for some end-use tooling applications. It can also be used in automotive and rail, depending on the mass of the model as well. So, you know, some industries have FXT requirements, and if it's less than a certain amount, you can then use it inside a car or in a rolling stock vehicle as well. So material validation, application validation is key to which machine and which material go for. This particular model, very complex, lots of thin walls in there. When you look at other systems out there, you may get prone to warping or distortion. We don't get that on our systems due to the thermal control and the way we extrude materials, but one of the key features is soluble support. Trying to build this and break away, inherently with FDM, you get some breakaway materials, you probably would end up snapping the thin features and it causing you problems, and it'd be unusable, you'd have to reprint it again and again. In this case, you stick it in a big tank. Basically, it's like a dishwasher tablet, you stick it in, you come back 4 to 6 hours later, and the support material would have dissolved, and you've got a functioning prototype or scaled mock-up or whatever it is that you want to use, in this case for a phonics for a car. Another example from McLaren. So these are end-use components done in nylon 12 CF. So if I give you that, give it a flex and a twist. Hopefully you won't break it. So nylon 12 CF has 35% chopped carbon fiber on the inside. We print about 98 to 99% fully dense. And when you look at other technologies out there from FFF, for example, like Mark Forge, where they've got an Onyx material, which is a nylon 6 with 15% carbon fiber. They have to use the continuous strands to reinforce the material to get the same stiffness. They are very strong on the continuous fiber, but basically when we print solid, we get almost the same mechanical performance, but you don't have 4 times X the build speed. You don't have the same issues when printing the models. So this is basically a torsion bar that I scaled up, so the smaller ones, just to show you the reduction in twist compared to ASA and other materials. This, however, is a gun shroud used in the pits at every race, done in 912 CF. It gets thrown around, drops on the floor. It's a very strong, robust material. Even so, at the bottom here, you can see some aerodynamic parts, end use, that go around the track on the F1 cars as well. So to give you an idea that you wouldn't typically use FDM, maybe for you think it's not fully isotropic, it depends on the orientation. We can control the rasters, the way the rasters are laid down. So we can do alternating rasters like when you would lay down carbon fiber that applies. Same sort of methodology here when you're processing the parts. Looking at the loads, the forces that applied will allow you to do some very funky end-use parts that can be used. Another example, I have 2 here. So this is a soluble core, or part of a soluble core. This is a layup tool. So different materials that we have give you different options. So this one on the screen is actually SR35 or QSR. It's a soluble support material, and some whiz or guru in the past came up with the idea of wrapping it with carbon fiber and then washing it out and being left with the carbon fiber on the outside. We since came to market with a material called ST130 that has a higher HDT of 120 degrees C. So I don't know why we called it ST130. But this one here basically is filament wound, and you dissolve the support structure out, or you can heat it up, make it malleable, and pull that out at the end, and be left with a very, again, free-flowing shapes that you couldn't machine or make traditionally, on mandrels and bladders and things like that. The other part that's going around the layup tool, that's done in a material called Ultem 1010. Has a very high HDT of around 213 degrees C, typically used for composite tools and aerospace medical devices. It goes into an oven up to about 8 bar of pressure as well, 7 to 8 bar of pressure, depending on how you're going to consolidate and cure. One thing that a lot of people say about FDM is the surface quality is abysmal. It depends on how you build it, the orientation. For the layup tool, you do have to post-finish it. You can machine it back, you can sand it back. So to machine it, it's very simple. We just apply a thicker wall thickness or additional contours, and you can set it up and machine it back. Again, you may have to seal the part depending on the application. So that's sealed with epoxy resin, or you could use model board sealer and sprays as well. So post-processing is a big part of the tooling application side of things. But here again, you can see just an example of the actual core. It's laid up with carbon fiber and then put end use on the part. So you're reducing the tooling times, reducing the cost. Makes perfect sense for McLaren with the volume of parts, but don't forget, every race there's something different on the car. So they couldn't afford to go and do the machining and the tooling in the traditional sense. Additive manufacturing makes perfect sense here. Also automotive dashes, panels, covers, all sorts of things. There's an example downstairs of one that's been laid up or covered with leather. Exactly the same thing. There are multiple automotive companies around the world using FDM for large panels and then wrapping them with carbon or leather or different fabrics, as well as there's also an example downstairs of polyjet printing onto fabric, which is also quite nice if you wanted to customize your suit or your evening wear or the inside of your car. You can do something if you so wish to do so. But again, different materials. There's also a material called Ultem 9085, which we use heavily in aerospace. It can be used for internal dash panels on aircraft, boats, all sorts of stuff as well. It's like a short, quick fire round of loads of different applications to get your thoughts going. This is with VAC mono, although this isn't the end use part. This was for trials and a mock-up that was done in 912 CF. So this is the air intake done on the full size of a F900, very large part. We're able to, on the dynamo here, can withstand sort of temperatures up to 140 degrees C. But for stress testing, putting it on airflow, there's a great video online where you can see the engine running and it's sucking in the air. So you wouldn't have done this in other materials, it would have been too brittle and easily broken, but this you can basically bang on the floor. As you can see by that torsion part, it's quite strong and good for testing parts as well. Automotive radiator ducting. So FDM, different materials have higher HDTs, but most FDM materials are good for -40 to -60 degrees C. So they can be used in some sort of, different challenging environments. This is actually one for one of our colleagues in the US who races a car and he had a bit of a smash. So he wrongly utilised the machine at the office and didn't get into trouble, but you can see here as an example. Also for defrost ducting, we've mentioned negative temperatures. So on aeroplanes, the Auto 9085 again, FST certified. End-use parts on planes, there are hundreds of thousands of HVAC parts, brackets, clips, ducting, other components on aircraft that are flying now, and you've probably been on a plane where they've been being used. But again, this one for matching the temperatures, but again, end-use applications. So whether it's an end-of-arm tool for taking parts out of a cryogenic container, that's also been done, as well as some really funky applications for Auto 1010 and 9085. So it was supposed to be automotive, but I thought I'd throw a tractor in as I'm the son of a farmer. Loads of things, doesn't have to be cars, it can be tractors, large fenders, archway covers, mirrors, again, brackets, headlight lamp housings and covers. So the part that you saw from Audi, just the lens cover, we also did in ASA assembly all behind it, so it can be fitted into the car. So it's a mishmash of technologies that give you an end use part. Now, additive manufacturing can't do everything. There are limits to what it can do. And I think I've sent round the actual wing drill guide that's got the metal inserts. I always say when I go to a customer site that end use parts or production tooling, a hybrid method is really good. So metal inserts, compression limiters, bushes and things. Because if you're fitting something to a vehicle or on a production line, as soon as you tighten it up, it doesn't matter which technology it is from a polymer point of view, when you torque it up, you'll more than likely crack it and it's going to be unusable. So you need to put compression limiters in. There's also been talk about consolidation of parts. Great, taking hundreds of parts and putting it into one makes it more simplistic. But what happens when that one part breaks? You've got to print the whole thing again. So modular components or printing parts that can be easily swapped out as part of preventative maintenance on a production line is also a really good idea. So things that commonly get broken, very easy to print as end use. On the inside, for contractors, camera housings, cable trays, vents as well, armrests. These are actually from the rail sector. So our materials are also certified for EN 45545-2 for use inside rolling stock vehicles. Cup holders, it could be done in ABS or TPU. So we also have a elastomeric based material that can be used. Something that Stratasys really wants to do is get a material qualified for a specific application within a specific industry like aerospace, like for rail, like for maritime as well. So looking at those standards, getting the parts sent off, the coupons sent off and tested. So like the Auto 9085, it's gone through EASA. We've got all the V-base allowables for it. So we know how that material performs in different orientations to give, we don't qualify the part, we qualify the machine to give you a realistic expectation of what can be done on the machine. FDM for tooling, why? Depending on the different technologies, I mean, originally we were just polyjet and we were just FDM. We brought on board the powder base, we brought on board stereolithography, as well as DRP. For me, I used to work at a different company for about 11 years before I joined Stratasys about 6 years ago. And being able to know what fits best, as you said earlier, where to walk away and say, look, we're not suitable is key. So for example, impact resistance, stereolithography is too brittle, so is polyjet. If you dropped it, there are some materials that are very stiff and strong, but again, inherently quite brittle. They won't last very long, whereas FDM, nylon 6, nylon 12 inherently have good impact resistance and can be used for different toolings, for different applications as well. The example at the bottom here is actually a thermoforming tool. So FDM again is hygroscopic and porous. It will allow air to come through. So in this case, we've used that to our advantage, allowing air to form through and draw plastic like Kydexes and things over the top. So if you've got a bridge tool or small volume production, you can do hundreds or thousands of these forms over the top of a 3D printed part, and it's cheaper if you do break it to print another one and stick it back in. Also can be used to simulate cold creep of the original metal tool. So again, it's a good way of proving an application and a process before going to the metal machining side of things for the end user. Some examples of that, so different automotive gauges done on the F717-900 for alignment, or drill guides for bonnets, for rear arches and vents and things like that on the side. End use on the production line, being used hundreds of times a day, being thrown around, and they're very, very usable and adaptable. So drill guides, for example, for United Launch Alliance on rockets, for the different launch vehicles, we do, or our customers do all of that sort of stuff as well. It's not just specifically for automotive. I'm going as quick as I can. Metal assembly tool, this is for a windscreen aligner as well. Again, 912 CS, really, really strong, really easy to lightweight and consolidate. Alignment here, different parts, as you would do with a traditional machine metal tool. You can put shimmies in to shim it up to make sure the alignments, there's no difference from really the traditional process to this. This is a hemming tool. So basically on your car, you put two sheet metals together, it hems, really high compressive strength. So, it's being used for that. Lightweight in the tool, making it easier on the production line as well. End of arm grippers, massive one here, loads of weight savings, means you can have a lower robotic arm, less preventive maintenance because it isn't as heavy on the end. You can consolidate all the vacuum lines on the inside and use that. Some great case studies out there, one from Halleman Titan, which is a good one. CNC, you need to hold something inside a CNC machine to machine it. Why not print the fixture? End use in there, being used all the time. Again, saves time. Again, if it's a really weird shape, it's nice to hold on to it with a good nesting feature. Almost done, last few slides. P3. So P3 is the DLP process, digital light projection. With the P3 machine itself, we have very, very high green states from the machine. So people like Henkel, Bassaf, and people like that use our machine to actually validate the materials for Photocentric, Form Labs, and other people. But because they don't have the same thermal controls or the same outputs, they get much less or lower mechanical properties. And they have to do longer post-cure processes, which causes warping and creeping, all sorts of stuff. But with our machine, you can get real use end use parts. And there's one here I'll send around quickly. Done in 3955 from Henkel. This material has a HCT of 280 degrees C. If you try and snap it, it's an end use part for a F-16 Falcon, so a fighter jet, for hydraulic lines, and also for fiber optic brackets and cables and things. There's other materials, there's loads of them. You can go into elastomerics, biocompatible, dental, hearing aid. There's quite a lot that you can use. And that's the example of the one that you can see there. So again, UL certified, FST compliant, very chemical resistant to hydrol, with the hydrocarbons and aviation fuels as well. And also we can print the elastomeric material that was also certified for end use. So looking at replacing all 10 phenolics and things like that. And that's it. Questions? Quick fire, lots of ideas, hopefully to see what can be done.
Obviously, you're using a lot of, replacing a lot of hand-laid composites. Have you used this technology with metal matrix composites?
No. Happy to. So my role is to work with the resellers like Laser Lines and with end customers to prove applications, new applications. I've been doing it for quite a while, and I love my job because every day it's something different, different challenge, different technology to look at. It's fun. So yeah, happy to play.
There's a big military using metal matrix composites. You can't take it from the lab. Used.
That's something you do?
I've done it.
You've done it, okay. I'll look into that. Thank you.
You mentioned that there was a biocompatible material for the 750.
Yes.
Is there a flexible one?
For the polyjet machines, yes, there is. It's typically used for hearing aids for the ends. So you can't do very large or thick parts because the tear resistance isn't good enough. We are working on other things, but currently there's nothing you can scale up to do larger parts. Just for soft tips for hearing aids.
Not for end use, like in larger parts.
Not for end use. It's the hearing aid one is end use. It's rated for mucous membrane contacts and stuff, but not for scaling up. No.
Okay. Good, is that it?
Thank you.
Thank you, Matt.
Thanks, man.
So we've heard quite a lot about materials and quite a lot of inspiring case studies and examples of where additive is being used, and a lot of it around specific technologies and specific materials. What we're going to do about next, Will Priest from the page, is going to talk about a very specific example where additive manufacturing is actually a game changer in changing the way we make things to improve their performance, particularly around thermal management.
That's it, yeah. Two myths. I'm not Mike Adams, I'm Will Priest.
Can I say Michael?
No, I've got Mike on my tag. And the second myth is it's not always lightweight. That is a Inconel 625. So that's fairly heavy. So if you're expecting something nice and lightweight, that's fairly heavy. But that's one of ours, which if you haven't seen it, I'll explain it in a minute. Okay, so realities and myths of additive manufacturing. I'm just going to kick off who we are, what we do, and then I'll talk through the myths as well. So as Kieron alluded to, we are specialists in thermal management, lightweighting, and we do this with AM, and specifically it's metal additive manufacturing. So everyone here has been talking about some polymers, metals. We're just talking about metals today. We're about 10 years old, so we're in that stage of becoming something quite big. We have direct investment from Renishaw and direct investment from Megit as well. And that's not only a financial investment, but a technology investment as well. About 35 people, crossing everything from analysis, design, FEA, CFD, applications, parameter development, which is something quite unique, is more often than not, we design ourselves into a manufacturing issue. So we need to work out how to get back out of that issue again. So we do all our in-house development of materials and machine programming. Test and validation, it's no good making a lump of metal if it doesn't work. So we're very strong on test and validation. We do as much in the digital world as we can, but I like making stuff, I like seeing stuff, and we like testing stuff because we like data. We do it on powder bed AM machines, as I say, direct investment from Renishaw. 500Q is the current gen machine with a 250, 250 build plate. So the volume is not massive, but as Kieron will show you, the machine is the size of someone's bedroom. And the next machine that's coming, I think it's got a nice big space downstairs, and that volume is 500 by 500 by 500. As James will tell you, there's machines already out there which can do it, but there's not machines that can do it down to the detail that we need to do some thermal management. In terms of key markets service, I can't tell you who our stuff goes on to, but we win races and we go really fast. It's proven high efficiency products. It's where we need to get rid of heat. We need to do it in a fairly small volume, and this is a really bad example, but where it needs to be lightweight as well. So that's one of our key markets. The other key market, which over COVID kind of went like that overnight, is aerospace. So this is where we employ a lot of the higher temperature Inconels and stainless steels. So this is where thermal is key on the hot side. So we're talking jet engines, talking bleed air coolers and the like. Weight is still an issue, but not so much in terms of aerospace as it is with the motorsport, but it's still a main KPI. Power generation, this specific example is from power generation. They're not too worried on the weight. The main KPI is all about performance. So it's efficient components, total cost of ownership. So say, for example, we've got an oil rig. They want to make that as small as possible, not necessarily as light as possible, but the most efficient that we can. High-end automotive. So what we do across all of these sectors kind of coexist and fall into each other's. From the motorsport world, we also do a lot in high-end automotive. So again, more space efficient, efficiency is needed, and where we want to get rid of heat, basically. In terms of in terms of what we do, we mainly focus on two elements. It's aluminium low temperature, air, water, air, oil, and heat sinks. We started doing a lot in terms of the electronics and EV industry, a lot of motor cooling, which I'll talk about later, which is really interesting. And then on the high temperature stuff, when things get a little bit warm, we employ Inconel's stainless steels, which we're still building in-house as well, designing and building. This bit's the boring bit about the business. Essentially, we look for problems and we look for customers with problems. They come to us. We have loads of smart people in a room, and there's other smart people in this room, which I like working with, and we come up with a solution. We do that alongside the technology and machine development. So as I say, we design ourselves into a manufacturing issue. So as we design things, we need to get ourselves out of that. So we get to a point where we've got a flexible solution for the customer, and then there's a number of different lines. We can actually do the production in-house. We've got a number of powder bed machines. You can either do a joint venture or a license, or you can take it away to the third-party manufacturer. Or what DMC and Kieron does is more of a virtual supply chain and bring them all together. Let's talk about some myths, because that's why we're here. AM is just another manufacturing process. I hate it when we get to the point with designers where we design something and then we go, oh, how should we make it? AM is a kind of way of thinking. If you're not thinking about AM when you first design a product, then you'll probably never use it because it's not the best way to do it. What you've got in front of you there is a high temperature combustor. So in the middle, there's a load of hot air that explodes up here. There's some injectors on the side. There's a load of heat transfer geometry and lattice here, all within one component. So when we start designing, it's all about thinking at a system level. So rather than thinking, what does the component need to do? It's about sitting with your customer or your partner, saying, what does the Formula One car need to do? What does the plane need to do? And then consolidating all of those things. So it's not just a manufacturing process, it's really a design process, it's a way of thinking. So when you brought up earlier about education, that's really key. You know, before I started working in the AM industry, I never really thought AM. I designed an AM before, but it was always a manufacturing process. It was always at the end when Prince of SMS to flying into rear wings. In terms of the benefits and what you can get out of it, you know, number one, it's increased performance. You know, what we employ are fairly small, fine lattices, so down to about 100, 150 microns on the alley and the Inconel side to promote heat transfer. It's obviously the reduced weight. So if we can get that weight down and you don't have to cart it around the globe, hours, days, years, and that brings down your total cost of ownership. Packaging is a big one. If there's any designers in the room, you'll know you'll get to a point where you're designing a plane or a car and someone's giving you this weird oblong shape you've got to fit your heat exchanger or motor housing into. And that's where we can come in, because we can build these shapes which you can't build any other way. Again, don't select AM because it's cool and it's the way to do it. If there's another way of doing it, if the customer comes to me, I will point them to a machine, and sometimes I'll point them to a casting approach. Lead time, it's not always, I'll talk about it later, but it's not always short. It depends what you're doing, and it's all relative to the actual design of the material. If we move on to the next slide, some recent examples, just to give you a flavour of what we do and how we do it and what can be done. You've probably seen this one in the previous slide. That one is a rocket nozzle in a high temperature Inconel. So that's the space and maybe even defence market. This one down the bottom, it's a bit of an ugly approach, but that is a test bed item for a cabin air cooler, so on the aerospace side. So in terms of what we're doing, it's kind of between that point of, I'm not going to say it's prototyping, it's almost validation before a lot of companies would get to the final solution. A lot of people are using AM for final solution, but not all the time. Sometimes it's just used for validation.
This one's really interesting. This is a IUK funded project. It's actually electric motor cooling. So again, utilising all the benefits of AM, so thin walls, complex geometry, to make a smaller package, essentially. I'll leave it there if anybody's keen to have a look at these. You're welcome anytime down to Haita, based in Bristol and Bath. Come and have a look at some of them because they're pretty awesome. Myth number 2, AM production is simple. It's really not simple. I was going to show you a nice 200-step routing of one of the parts as it comes off the machine. I got told off this morning, I'm not allowed to. Essentially, the first 2 steps of that process are load to machine, press print, and then you're done, right? No, there's 100, 200 steps after that if there needs to be. You've got to think about powder removal. Hopefully the guys at DMC will show you later. Essentially, with metal AM, you're building a massive vat of powder, and you'll design the thing, but then you've got to design the powder out, essentially. You've got to get the powder out of something like this, which is really difficult, right? When you're making thin wall channels, you've got to get the powder out, which again, you design yourself into a manufacturing. Support removal. Again, we can make these amazing complex shapes, but we can't just build them in thin air. We've got to actually implement support structures to build upon. So this one here is what we call an E-stage support. It's basically like scaffolding, which actually we support the part on. So you've got to think about the whole manufacturing process as the design. You've got to get it off the plate. It can be really complicated. The way that the process brings itself together, we're firing a lot of lasers, a lot of power into the part. Essentially, when you chop that off the build plate, it all could go this way, that way. You know, you've got to do stress reliefs. You've got to think about how the residual stress is in the part when you design it. And again, you've got to think AM. So you've got to do a lot of that modelling when you're actually designing it. It's not a case of just whipping up some CAD and printing it. It's a case of doing all the right validation before you get there. Again, I really wanted to show you the routing because the post-processing, you know, a lot of the parts will have a post-machining on. This turbine housing, essentially interfaces where you can't get the surface finish yet. I'll say yet because it's going to happen soon. We have to post-machine and post-finish interfaces, mating surfaces, shafts. And again, validation, you know, you've got to check the parts are good. You can't just push them out the door. At the moment, there's a lot of CT, X-ray scanning, a lot of leak testing, dimensional analysis, and it's quite a controversial item in the AM world. Is how to qualify these things for aerospace, how to qualify them for nuclear, space, etc. Because there's so many steps to the process. Ultimately, as well, AM, the actual AM part when we build it, can only account for 30–40% of cost sometimes. There's so much cost in the post-processing. What we're trying to do and what the DMC are trying to do is make that transition efficient and as cost effective as possible. And ultimately, we can try and reduce all of those steps if we can. If we move on, the more complex we get, people think it gets wildly more expensive. I'm not going to say AM isn't expensive because component-wise, sometimes it is. The total cost of ownership, when you think about how much you're transporting around the world, how long you drive the car for, it can be cheaper. But once you start to build, if I build this part with no lattice in it, so essentially if I build these outer walls, inner walls, it doesn't cost me much more to build the complex shape and geometry into that. Extra complexity is little to nothing reduction, but gives you the ultimate value. As a designer, you've got to think multifunctional. This lattice inside, it's a heat transfer geometry, but it's also structural geometry, and it also has many other characteristics which I'm not allowed to tell you about. So again, design, you've got to think about the whole product life cycle. You've got to think about educating. If you're doing it, educate the designers about how to do it. If you want to talk about AM and how to design for AM, come and have a chat with us. I'm happy to talk around it. As well, you know, there's big data transfer in all the things we're doing. There's challenges moving forward in that. There's designing for thermal stress, as I say, during the build. You've got to think about how you're building it in terms of orientation. So not only for quality, but also for cost. So the best way to build that for quality is that way. I can only fit one on a plate, which is rubbish for the cost guys. They want to build 5 of them like this on a plate, because the moment you fill that build plate, cost comes tumbling down. But it's still expensive at the moment. But yeah, watch this space in terms of that. As I say, multifunctional as well in the manufacturing phase. We actually use the support structures as thermal transfer units in the build. So again, not only you're designing the product, but you're designing the manufacturing plates around it. That is a, oh, I didn't know that was going to play. I thought it's a picture. So that is actually this part from the build chamber. You might see it later downstairs, but essentially you've got a 30 micron layer powder, and then you've got 4 lasers in each area of the chamber, actually melting the powder there. And when, I don't know if it's shirt, when it's finished the layer, essentially the bed drops, a layer of powder comes over, and then we all start again. As I say, you can easily design yourself into a manufacturing issue, and some of our most complex IP is actually around how to make it, not how to design the shape. I've kept it fairly brief. Thanks for listening. Any questions, come and have a chat with me. As I say, you're welcome down to Heights at any time. We're based at Bristol Bath Science Park or in Thornbury, so not a million miles away. But yeah, come and have a chat and come talk AM and see some of the machines. Thanks very much. Any questions? Good. Thank you very much.
Right. Agenda next is to have a look around, I guess.
Yeah,
Let's do a wrap up.
Yeah, do a wrap up and then you put on some food and some tours, right? So
Is there more food?
I think so. Isn't it?
Yeah. I mean, I don't know whether anyone's got any more questions or any conversation that comes out of this, but I think it's been an interesting set of presentations that give us some feeling of what AM is being used for at the moment. There's still the word prototyping being used a lot, which I'm trying to get away from. No. Product development iteration, but yeah, you know, there's a lot of opportunity around additive manufacturing, but our focus here is to try and get people engaged in designing for additive. I think Will and others mentioned it. If you're not thinking about designing for additive right at the beginning, you're probably not going to find additive manufacturing as a useful solution, because it's got to solve problems that can only be solved with additive. If it can be solved with traditional manufacturing processes, you're probably best off continuing down that route. I think there's some interesting areas around thermal management where it's a game changer, isn't it, in terms of thermal management, but it comes at a cost. So it's in certain markets that can adopt it. And the one that's commonly overlooked is jigs and fixtures, and sort of manufacturing process, part of the manufacturing process rather than end-use parts. Everyone's focused on end-use parts, but actually there's lots of opportunity there for jigs and fixtures and tooling. What we'll do is I think we'll probably split maybe into 2 groups when we go downstairs and have a look around. I don't think there's certainly nothing down there that anybody should take photographs of, but I don't think there's anything down there you need to be concerned about from a confidentiality point of view at the moment. And I think we'll probably get Nigel to come up as well to take one of the groups around it. Has anyone got any more questions? Otherwise, we'll close. Brilliant.
Thank you very much.
Thank you. Thank you.
So Kieron, Matt, and Will, if you could stay behind.
Again.
Yeah, please. Yep. And if everybody else, because I think Nigel and Kieron have put on some food, I believe. So please help yourself to that. Definitely, there's more teas and coffees, and then Kieron and Nigel will sort out all the tours and stuff. So thanks for coming along and enjoy yourself. And that concludes proceedings online for us as well. Hopefully you enjoyed it. I mean, as per usual, we'll do an email with the recording and the slides to follow up. But yeah, hopefully you find it an interesting event, and we'll hope to see you in the next one. Thank you very much. Bye-bye.